Yesterday we introduced sensitivity analysis as a way to evaluate the effect of uncertainty in decision making. And you remember that we decided to introduce perturbations in the parameters of the objective function. And we found that if we perturb the parameter, the optimal decisions to be taken changes, and the related benefit changes as well. This analysis is very much useful to understand what is the effect of uncertainty, what is the impact of uncertainty on the decision, but still doesn't give to us any indication on the most appropriate decision to be taken in the presence of uncertainty. After this assessment, you may wonder then what is the best, the optimal value for the allocation, because you see that depending on the perturbation that you introduce, the optimal allocation changes, and therefore you may wonder what is, at the end of the story, the allocation that you should give to the user. The problem is that sensitivity analysis is, in this sense, is limited, because, as I said, it gives you an indication of the impact, but doesn't suggest any solution, any optimal solution. So, at this point, we have to introduce a criteria for decision making under uncertainty. And I want to give you an example which refers to this exercise here. You see that for each allocation, you can compute, maybe that it's better if I show you the other table, this one. For each allocation, you can compute the benefit that corresponds to that allocation and corresponds to the perturbed value of the parameters. We did so in this column here. Now, we could integrate the information by checking for each allocation that we consider here, what is the benefit for each one of the configuration that we have selected, for each one of the perturbed configuration that we have selected. So if I choose, for instance, the allocation of 38, which is the optimal one when we do not perturb the parameters, we can of course compute the benefit that corresponds to that allocation and is computed with the unperturbed values of the parameter. But we could compute also the benefit that corresponds to the allocation of 38 and each one hypothesis of perturbation of the parameter. So we could, as I said, integrate the information by checking what happens to the benefit for each one of the considered allocations and each one of the considered parameter set. Therefore, I should compute the benefit for the allocation of 38 that I get when I perturb by augmenting 25% the parameter A, and then I compute again the benefit for perturbation corresponding to a decrease of 25% of parameter A, and then I compute the benefit that is given by increasing B 25% for each one of the perturbed configuration. And therefore, I could identify, for instance, the minimum. So for each one of the allocation, I could identify the minimum benefit that I could get for each one of the considered perturbation. And this could be repeated for all the allocations. If I want to be safe, a criteria to decide could be what is called the maximum of the minimum. So first criteria could be what is called the maximum of the minimum, which means that you select the allocation that gives to you the maximum benefit in the worst case. I try to explain better. As I said, for each allocation I can compute all the benefits that I get for each parameter configuration. I estimate for each allocation the minimum benefit that corresponds to any assigned value of the parameters for any assigned perturbation, and then I select the allocation that gives to me the maximum of the minimum. This is a criteria, it's just an example of criteria. That is called the maximum of the minimum. This is of course a safe option, which nevertheless is a bit limited, as you can understand, because if I'm willing to take some risk, this is not considered by this option. So this is a safe selection. But it's meaningful because it gives to you an example of a criteria that in the presence of uncertainty can help you to select one specific allocation according to the results of sensitivity analysis. I didn't compile a table with this, so I can't tell you in this case what is the resulting allocation. There is not enough information here. We should complete this table. Probably it's not easy to keep it in a table, but we can, for instance, add one more column with the minimum benefit that corresponds to each allocation, and then you take the maximum of this minimum. You could do it yourself. It's very easy, as I hope you understand. Now, this criteria, as I said, is not really complete because it doesn't allow us to take into account our propensity to risk. It's just a safe option. So in order to take into account the propensity to risk, which is very much important in the presence of uncertainty, because, you know, we cannot always take the more safe option. Sometimes we have to take the risk. Even when we design structures for given forcings, for instance, forcing due to snow, due to earthquakes, and we cannot always take the most safe option because the safest option, if it exists, involves an oversizing. So sometimes we have to take the risk. For instance, in hydraulics, when we design the bridges, we take the forcing that has typically a return period of 100 or 200 years, which means that I take the risk that on average, once in 100 years or once in 200 years, the bridge collapses. So this means taking the risk. And when I select this return period, when I say that I design a structure for a return period of 10, 50, 100 years, I am evaluating my propensity to risk. For instance, when I design a dam, I want the return period to be typically 1,000 years. They are designing now a new dam on the Nile River. They want a return period of 10,000 years, which means that they are not willing to take much risk. But when we design sewer systems, fognature, for instance, the return period is about from 2 years to 10 years, which means that we are willing to take the risk. And we are willing to take the risk because the consequences of a failure of the sewer system are not so, of course, so severe as the consequences of a dam failure. So even in this case, we need a criteria that allows us to, in decision theory, to take our willingness to risk into account. And in decision theory, the most classical approach to do that is to make reference to the utility theory. This is the subject that I'm starting now, which is, I think, which is for sure very much important. And I think it's also an interesting subject because this really opens the possibility to evaluate how much people are willing to risk and therefore to incorporate this willingness, this information in the decision process. Now, Okay, you see that in this slide here, I gave again the example of the maximum and the minimum, and let now me move forward with the utility theory. The basic requirement for the utility theory is to assign to each possible decision, and therefore to the related benefit, the value of a utility function, a value that is called utility. And now we have to understand what is this utility and how to compute it. First of all, let me say that this number, this variable called utility, is varying between 0 and 1. It's just a decision to make it variable in this range. And therefore, depending on the value that it assumes, we must quantify the utility of a decision. Like the allocation of 38 in the present case, in the previous case, I have to assign a utility. Utility means a measure of how much I like this decision. And when I say how much I like, I have to take into account the risk, because any decision is risky, of course, because if you give less water, it's risky because you don't get enough money, you get less money, so it's risky. If you give too much water, it's risky because you may run out of water. Therefore, you always have a risk, and when you evaluate how much you like a given decision, of course, you take into account the risk. If you don't want the risk, you like safe decisions. If you like the risk, which means that you like money and therefore you are willing to take the risk, then you like risky decisions. So now the issue is how to assign this utility. First of all, let's define some axioms. In order to define utility, let's define some axioms for the value of utility. First of all, I said 0 is minor or less than utility, which is minor or less than 1. This is the first axiom. And the second axiom is that, first of all, let me make a premise. The utility depends on the decision. Let us assume that we can then quantify the dependence of the utility on the benefit of the decision. The decision is X. Let's compute the benefit associated with the decision, and then let's define the utility depending on the benefit. This is useful because, of course, when we decide how much we like a decision, it's difficult to say how much we like 38 liters per second of water. It's easier to define how much we like money, a given amount of money. So in order to define the utility, let's assume that we define the utility depending on the money we are expecting from a decision. Okay? And therefore, let's say that another axiom is that the derivative of the utility, which depends on the benefit, the derivative with respect to the benefit itself is positive, which means that the utility is, or let's say is, we can allow the equal sign here, which means that the utility is a non-decreasing function of the benefit. This is another axiom. So, what should we do then? Identify all the possible decisions, and therefore all the possible allocations which are interesting for us. Compute the benefit that corresponds to these allocations and then define some utility of these allocations through the benefit. Now, what can we understand already now? That, of course, the utility is an increasing function with respect to the benefit, but there are many different ways to increase. The utility can increase very rapidly for increasing benefit, or can increase very slowly. What does this mean? If the utility increases very rapidly, so that I get close to 1 for low values of the benefit, it means that I am a prudent person. It means that even low values of the benefit are fine to me. Remember, high value of the benefit means high risk. Low value means low risk. Therefore, if you say, okay, I'm happy to give to a low benefit a utility of 1 already, this means that you like low benefits, which means that you don't like risk. The opposite. If you give high value of utility only to the top benefit, means that you are looking forward to the maximum, and therefore means that you are willing to take the risk. So we have to find a way now to quantify this, because otherwise, of course, it's arbitrary. We have to find an objective way to define the utility. So let's suppose that we have a problem to deal with, and I will show you an example in a few minutes, which is different with respect to the previous one because it's a bit simpler. The previous one with sensitivity analysis was a bit complicated, too many options. You have to make reference to a problem, identify all the possible allocations that are interesting for you, and this is quite easy because depending on uncertainty you will see that it's quite easy to identify, provided that you can identify uncertainty, you can estimate uncertainty, it's quite easy to identify the options for the allocation that are interesting for you. So we have to identify the options, the possible choices, and then we have to identify the benefit that corresponds to any choice, any possible allocation, any possible decision. And therefore, once that we have identified the benefits, it's clear that we will be able to identify a minimum benefit and a maximum benefit. And of course, you will be able to identify a series of benefits that are in between. Because you select a finite number of decisions, like 10, and therefore you will be able to identify possible values for the benefit. They might be more than 10, because if your parameters are uncertain, you can use different values of the parameters to compute the benefits, and therefore you may have possible benefits that are in a higher number with respect to the possible decisions. We will see the examples, because if you have uncertainty, of course, for any decision, you can compute the benefit in different ways, depending on how much you change the parameter, depending on different values of the parameter. But in any case, you will end up with a finite number of possible benefits in which you can identify a minimum and a maximum. And therefore, now our task is, for all the possible benefits between the minimum and the maximum, to assign a utility. In an objective way, let's say in the most objective way. And to do so, we need to provide now a definition for utility, a definition that must satisfy the axioms and is, in a way, as much objective as possible. Now, let me introduce the definition, which later on I will show you on the slide, but I prefer to concentrate on the blackboard now. I deleted the axioms, but of course we can remember them very well. And now, let's concentrate on a given benefit value between the minimum and the maximum. Let's say that is in between. So let's concentrate on a value MB x star. Just one, because we can repeat then this same evaluation that I'm now explaining to you as many times as we need. So let's concentrate on this given benefit and let's ask ourselves this question. Let's put ourselves in a situation where we have to decide between two possibilities. Again, in order to simplify the problem, we decompose a complex decision in a sequence of decisions between two options. This is again the principle of the pairwise comparison. We have a complex decision to take with many options, and then we decompose this complex problem in a sequence of decisions between only two options. Now, for the given benefit, then, let's concentrate on two options. The first option is to get the given benefit and the x star for sure. The second option is to take NB max with probability small p, which means that with probability p varying between 0 and 1, let's define this capital P, sorry, not small. With probability p varying between 0 and 1, in the second option I get the maximum benefit, which means that is higher than the benefit MBX star. But then the question is, what happens in the second option if I fail in getting the maximum? Correct. If you fail in getting the maximum, you get the minimum, which then is obtained with the probability 1 minus p. These are the two options. So the first option you get for sure the benefit MBX star. In the second option, you have a probability capital P of getting the maximum, and if you fail, you get a probability with probability 1 minus P, the minimum. Therefore, you have to decide which one would you choose. It's clearly depending on the probability P. Because if I told you probability P is 1, then you would select a second. Because this means that you would for sure get the maximum, which is preferable than getting for sure a lower benefit. And if I told you that the probability P is 0, you would for sure select the first option. Because probability 0 means that you for sure get the minimum, which is lower than the given benefit. So the moral of the story is that depending on the value of P, you would select 1 or 2. And you also can understand that your choice depends on your willingness to risk. Because there might be people who would say, I prefer to take the risk. Even if P is low, I prefer the second option, because I would like to have a chance to get the maximum. If you are instead more prudent, you would say, no, I want a very high probability P to prefer the second. So your preference is dictated by the value of P and your willingness to risk. And there might be a p-value where you cannot distinguish between option 1 and option 2. They are equivalent to you. It could be 50%, it could be 60, it could be 70, it could be P, could be 0.2, 0.3, 0.5. In percentage term, could be 20%, 30%. And this depends on your willingness to risk. So the p-value which makes you equivalent. The two options depends on your willingness to risk. This p-value is finally the utility of NB star, utility of NB X star is defined as the p-value that makes the two options equivalent. And this is what you find in this slide. Of course, I said that this is an objective criteria for identifying the utility. You could say it's not objective because it depends on myself. So if I define the utility myself for a given problem, and then I ask you to define the utility, your definition will be different from mine. So this is a criteria to define utility, which is fairly objective, but not strictly objective. But at the end, of course, given that the decision depends on our willingness to risk, it's never an objective decision. It's a subjective decision. But still, this way of defining the utility is quite objective, let's say. At least we have a criteria, well-defined criteria to identify it. Okay, what happens then when we have defined the utility of different decisions? First of all, let me note that we can draw a graph representing the utility depending on the benefit of the decision. So if we want to draw this graph, where here we put the utility and here we put the benefit, for sure the utility function varies between 0 and 1 and varies between the minimum benefit to the maximum benefit. So you have to assign utility 1 to the maximum benefit, utility 0 to the minimum benefit, and then you can have different shapes like this one or like this one. This is more prudent, this is more willing to risk. Okay. Now, let's introduce an example, as I said, which is the same objective, the same benefit function that we had before, we had yesterday. And for the parameters, let's reduce the possible options. Let's assume that the parameters can just assume 3 different configurations, which are given here. And each parameter vector can occur with equal probability, which means that we have a probability of 1/3 that the true parameter vector is W1, probability of 1/3 that the true is W2, and probability of 1/3 that the true is W3. And this is clearly a problem where you have uncertainty. Like before, the parameters of the objective functions objective functions are not exact, they are defined with some uncertainty. Now, what happens here? First of all, what are the interesting options for us, the interesting allocations? Of course, in this case, let's assume that our aim is to maximize the benefit. So to find the allocation that maximizes the benefit. And if there were not uncertainty, it would be easy to find the maximum. We already know how to do that by simulation. We tried yesterday, very easy. But given that we have three possibilities for the parameter values, this means that we have three candidates for the optimal allocation. So when we want to identify the interesting decisions for us, for sure, we will have to consider the three allocations that give the maximum benefit accordingly to each outcome for the parameter vector. So the first thing that we have to do, again, is to identify the interesting decisions for us, the relevant decisions, and for sure, this relevant decision will include the allocations that give the maximum benefit accordingly to these three parameter sets. These are the three objective functions from which you can identify the three objective functions, for each one of the parameter vector that I showed you in the previous slide. And from this objective function, you can identify the optimal decision for each outcome of the parameter vector. And this can be done, as I said, very easily, as we did yesterday. And if you made the computation yourself, you would find that these optimal decisions are the ones that are given here. And I added another one just by chance. I picked it up. So the three optimal are 28, 38, and 42. And then I just consider 30 as a fourth one. Because, of course, you may be interested to see what happens for an allocation that is different from the optimal ones. There might be many reasons for you to identify more options. In this case, I just put the fourth one here. And you see that the allocation of 28 gives, it is the optimal one for the parameter vector W1. So if you change the parameter vector, you get lower benefits. Because, yeah, it's not indeed true, you could get also higher benefits, so it's not a requirement. But in any case, you get a different benefit. Of course, you change the parameter vector, you get a different benefit. The allocation of 38 is the optimal one accordingly to W2, and the allocation of 42 is the optimal one accordingly to W3. Here you see a case in which, indeed, if you change the parameter vector, you get higher benefits. Of course, you get a different benefit. It can be lower or higher. And then we have this fourth option for which we can compute the benefits related to each parameter vector. The fourth one is not optimal for any one of the parameter vectors. It's just, as I said, a decision that I identified by chance. In doing so, I have identified 12 possible benefits which represent all the possible outcomes to which I am interested in. because 4 decisions that are relevant to me times 3 parameter vectors means 12 possible benefits. Now, my task is to assign to each one of these benefits the utility. I can see that 79.22 is the maximum, if I'm not wrong, yes. And I can see that 61.18 is the minimum. So I already know that I will give utility 1 to this benefit and utility 0 to this one. And then I have to define all the utilities in between. Let me just note that we can compute also the average benefit and the minimum benefit. So if we want to adopt the maximum of the minimum, look at the table and we would choose allocation 42, which gives to me the maximum of the minimum, which is the first criteria that we considered, that doesn't need any definition of utility to be computed. Or we could choose, for instance, the maximum of the average, which, as I said, may be not a perfect choice, because it would be too risky. But if we decided to take the maximum of the average, then the optimal choice would be the 4th allocation. So, this example also shows you that in this case, in which I decide to select my option with the average benefit, it's the 4th decision that I picked up randomly that turns out to be the best one. So the examples also tells you that the best decision is not necessarily